So good afternoon again. My name is Martin Rups from the Technical University of Denmark. I'll chair the session. And it's my pleasure to announce the first speaker of the session, Professor Sandoghdar, from the Prime Institute in Erlangen. And the title of his talk is the one-dimensional controllable horizontal system. Order to disorder.
Yeah, thank you very much for the introduction, of course, for the opportunity to contribute to this great meeting, which unfortunately I've been missing. I had to be in Erlangen yesterday, and that was kind of a killer for a workshop like this. I tried to pick the topic from a group that would fit best the topic of this workshop, and it connects very well to several of the talks that have been given this afternoon. So before I move on, I'd like to acknowledge people who are working in the group, working hard. Many of them are working on projects that will not have anything to do with what I tell you about. In particular, half of the group does biophysics now, and that has nothing to do with what I'm going to tell you about. Considering this fairly specialized workshop, I'm not going to give you a general introduction of why we're doing what we're doing. I just assume that you would appreciate our general effort if I say that we would like to take light matter interaction all the way to the very small scale, and in particular to the interaction at the level of single photon, single emitter. So this is generally what we would be looking at. As you will see, our emitters will be quite often organic molecules, which provide a very good two-level system, optimal two-level system, and we want to get to a point where we interact with them via individual photons. Now, of course, if you do that, then you're kind of more of a long-term goal, maybe, is to get interaction of a network, starting with something like 2 atoms and 2 photons. We would like to do operations, get cooperative effects and all of that. And of course, in the kind of very long term, you would like to scale that up as much as you can. So the question is, how does one do that? There are lots of challenges, of course, from an experimental point of view, but we've spent a lot of time just worrying about the very basic question, which is how efficient is the interaction and what you have to do in the lab to actually worry about the first building block of getting an atom to interact with something like a quantum emitter. So it was mentioned in one of the talks this afternoon that there are different methods. One of them, for example, is strong focusing. This is what we have been working on for more than 10 years now, so I'm going to give a brief overview of that work and tell you how that has led to what we're doing today. So if you want to investigate this very simple scenario of light field strongly focused on something like an atom, you have to pick your experimental system. Maybe the most obvious thing would be to pick an atom, but because an atom likes to diffuse and move around, you have to go through the trouble of trapping this atom, and of course that has been done, but that has its own kind of difficulties because you have to keep the atom within a few 100 nanometers fixed if you want to do that experiment. Our route in our lab has been coming from the solid state side, and so if you work in the solid state, you would have, let's say, a whole bunch of emitters. This might be different things, but whatever you do, you have to go to low temperatures if you want to have a good optical transition. So the emitters that we will be using will be often this type of aromatic molecule, and like I said, we have to go to low temperatures, so the price that we pay is to do cryogenic experiments. As I said, the emitter can be many things, so this is kind of our decision of what you want to do. You want to have something like a crystal with a whole bunch of emitters. You want to talk to individual ones. You want to address the individual emitters with your light field. Molecules were the first ones that were addressed at the single emitter level, but soon quantum dots came in, and of course, I'm sure you're all familiar with the color centers, and recently we showed that you can also do this with rare earth ions. So I'm going to introduce two basic systems and then talk about the real experiments. So for those who haven't done much of solid-state spectroscopy, single emitter spectroscopy, this is the kind of an overview of how you do this. So you start with a sample that is fairly highly doped with your molecules, and the molecules that we're talking about, you can imagine to be a kind of a piece of graphene that is very carefully cut out. Of course, this thing is done by chemical synthesis, so you can have large amounts of it without a problem. These molecules have, just like any other dye molecule, electronic ground state and electronic excited state. What you have to keep in mind is that you always also come with vibrational levels. The vibrational levels in the solid state are quite different from the gas phase. In the gas phase, the vibrational levels are long-lived, but in the solid state, they're extremely short-lived, which means that when you go to the upper state, you can decay by broad transitions to these levels. That's your kind of broad fluorescence that you would get. But you can also come down via this main transition, and this transition can become at 1.5 Kelvin as narrow as about 20 megahertz, which is really just a Fourier transform of 10 nanosecond spontaneous emission lifetime. So these systems turn out to be really good optical two-level systems. Depending on your choice of molecule, you can put your wavelengths at different places, and you essentially have a molecule for every alpha-like atom that you might like. Lithium, rubidium, sodium, you always have a molecule that is also at that transition. So the way you choose or you select a single molecule is now a whole thing. You take advantage of the inhomogeneous distribution of the resonances because each molecule seeks a slightly different local environment, and its resonance is shifted with respect to its neighbor, which means that when you scan your frequency through the inhomogeneous band, you become resonant with individual molecules at different times. But if you zoom onto this spectrum, you see that you have a collection of lots of very narrow, well-defined Lorentzian lines. The signal-to-noise ratio is extremely good, and again, I emphasize that the line width that you see here is the line width, the so-called zero phonon line. It's exactly what you would expect if you take 1/2 pi of 10 nanoseconds. So there's no dephasing that you have to worry about, although you're working in a solid state. And of course, the advantage of working in a solid state is that your molecule sits exactly where it should be sitting, and you can come back to it tomorrow or in a week and do exactly the same experiment with it. Perhaps another thing that I have to emphasize is that although you're talking about molecules, these molecules do not photo-leach. You're working at 1.5 Kelvin, so the kind of things that you might have heard from some talk or somewhere that molecules photo-leach, they do not apply to the system. This is a very well-defined system at the end. So in the lab, this is the kind of a video that you might record. Time in this measurement is frequency, so the frequency of the laser scan, and you're looking at a part of your sample, so you see that you become resonant with individual molecules that are sitting randomly at different places, and each of those corresponds to the sharp type of 20 megahertz line. Okay, so that's kind of how single molecule spectroscopy works. So once you have a video like this, you have all the information about the molecule, you know where it's sitting, you can find the orientation of its dipole moment, and you know at what frequency it is. So you essentially characterize your sample completely, and you can come back to each molecule anytime that you like. The molecules are extremely good as two-level systems, but they're not very good as, or they're not good at all as three-level systems. For example, if you are looking for a lambda transition, this is not easy to have because the ground state has no relatively spin, and you essentially only have one ground state. So that's why we've been interested in rare earths. Rare earths are also a solid-state system. They're well known to be extremely photostable. Of course, you know them from your laser crystal. You can zap them for decades, and they still are very photostable. They have the advantage that because they have intra-F transitions, they're well shielded from the environment, and they have a weak transition. They don't emit a lot of light because the lifetime of the excited state is very long. But they have a wonderful atomic structure, something that no other solid-state system basically can offer. So you really have well-defined hyperfine levels associated with your various states. So we worked very hard for several years to show that the same procedure that I just showed you for molecule spectroscopy actually also can work for rare earth ions, but this is now essentially a new field. What I'm going to show you about molecules, essentially you can imagine in the next few years we can also do with these rare earth ions, with the advantage that you have very well-defined transitions and extremely long-lived hyperfine levels. The coherence times of these states can go up to hours. So that was a little bit of an introduction about the kind of system that we have. Now I'd like to show you some of the basic physics that we've explored. Again, this is the kind of thing that we started to look at. It was mentioned in a previous talk that the cross-section of a tunable system is as simple as lambda squared divided by 2 type of thing. So it's a large cross-section, and that's why you think that if you focus down to that type of area, you should have a very efficient interaction. This cross-section in the solid state is usually worse because you also have to take into account this ratio of gamma 0 divided by gamma, where gamma 0 is your natural line width and gamma will be the overall homogeneous movement. So if you have any type of boson coupling, your cross-section goes down. And at room temperature, the penalty that you pay is of the order of factor of 1 million. If you go to low temperature, you can take this to be reduced to 1. So keeping that in mind, we started doing experiments again more than 10 years ago, and this is kind of a summary of the type of work that we published, basically demonstrating that yes, it is possible to get a very strong interaction simply by focusing light onto a single quantum emitter, a two-level system. So this is an extinction signal that you will be recording, and you can see that you are getting attenuation of the order of 10-20% by simply putting a single molecule in front of your light. And that's all because your extinction cross-section becomes so large. Now, it's also important to remember that extinction is an interference phenomenon, right? The way you come to explain your extinction cross-section is that you basically say when you illuminate that you have the probability of not interacting with the molecule and the probability of interacting with the molecule, and you add up the fields, then you square them, and the total intensity that you get, that's this cross term, and that's the cross term that leads to this destructive interference in the forward direction, which means that ideally all your light is reflected backwards. But what you have to remember is that the mode of the incoming light field is not automatically matched with the mode of the light that is radiated, because your atom lights are radiated like a dipole, and those two wavefronts are not matched, which means that if you just shine light at your atom, you don't get a very large effect. That's why you have to do tight focusing, put most of your light into the dipolar field, and then you get a good interaction. But what that also means is that you can now try to think that maybe you can use clever ideas for example, from antenna theory, to modify the radiation pattern of your atom so that you can match the mode of the atom to the mode of the incoming beam. Before I get to that part, I'd like to show you some new results where we have also demonstrated that this strong interaction that we already have in the tight focus can also lead to a very efficient nonlinear type of interaction. Basically, the idea is that if you think that you want a nonlinear process, you typically, in a kind of a naive discussion, you would say you need two photons to come at the right time in the right place and be mixed by a nonlinear medium. Now, of course, we all know that a two-level system is a pretty good intrinsically nonlinear medium. Now, if you can manage to funnel each photon onto this individual molecule so that that interaction becomes very efficient, if you manage to put two photons at the same time, then you would expect to get a strong nonlinear type of effect. So this is an experiment that we tried, so I won't go into the details of the technical details. Basically, we're doing this transmission experiment, but we're focusing tightly onto our molecule. We have a pump and a so-called probe, but actually both of these beams are extremely weak. So this is a quick, brief overview of what we can do. If there's no pump, this is the resonance of the molecule. You see that in this case you're seeing a dip that is only of the order of 4% in this experiment. But if we now introduce a weak pump at slight detuning and with a very low Rabi frequency, this Rabi frequency is now basically of the order of gamma, so not a very strong pump. You clearly see now the evidence of something interesting happening, a lot of new frequencies being generated, and if you increase this Rabi frequency now a little more, it's still not very high, but something of the order of 2 gamma, then you clearly see various features that you can associate to things like a 3-photon amplification and stimulated radio scattering and that kind of stuff. So the physics of this, of course, has been known from a theoretical point of view from the 80s, but this is the first time that we think someone has done this at a single molecule. And what's interesting is that if you now do your math, you see that you really need just a couple of photons to arrive there, and you already see this type of effect. So you can also now, of course, now that you have nonlinearity, you can imagine that you do photon switching. You would switch one beam by tuning the frequency or amplitude intensity of the other field. This is what we've done, so you can imagine that when the pump is off, we're seeing the signal on resonance, and when we turn on the pump, the extinction goes away, and so you can come up with some kind of a figure of merit for the kind of switching contrast, which would be shown by this red figure. And theoretically, you can show that if you really had not just 4% coupling, but much higher coupling, you could get extremely efficient switching. All right, so this was all done with laser light, and in principle, you want to do this at the single photon level. The way to do this then would be an experiment like this, because the best single photon source for you would be a second molecule that emits single photons at a time. So the idea would be to couple two molecules at a large distance, and we still use a kind of free space wiring, which is nothing but focusing and collimating light. This is an experiment that we've done several years ago. I just summarized that, so you really can do this experiment today in the lab. You take one microscope, you excite the molecule the way I've described to you so far. That molecule emits photons. These photons are now Fourier limited, so they're very narrow band. This is an anti-bunched field that is propagating to a large distance of a few meters. Then you focus that again onto a second microscope in the cryostat and focus it onto another molecule and look at the detector. Of course, at this point you have to tune your frequency, just like we do in any kind of a spectroscopy experiment. And we do this by putting electrodes, microelectrodes, and start tuning the resonance of one molecule with respect to the photons or with respect to the other molecule. And when you do this, you can record a signal like that. So you really see now that you're monitoring or observing the extinction of a single photon stream by a single molecule. Good. So I'm not talking about the efficiencies. There are lots of technological things that have to be improved if you want to use this as a kind of a workhorse. But we've already thought about what happens if you get all these things done. How do you scale up? So this is basically where you would want to go. And at that point, this strategy of free-space wiring would not be very practical because it would involve a lot of very efficient focusing and collimation, and that's not a very efficient process. So at that point, we thought that we take advantage of some of the ideas that have been around in terms of, for example, coupling your emitters to this type of subwavelength waveguide. This subwavelength waveguide in our language is basically a nano antenna that forces the atom not to emit in 4 pi, but it forces the atom to emit in a well-defined mode, and therefore now that emission is well mode matched with the photon that will be propagating along that mode. So now you can imagine that all the physics remains the same as in tight focusing type of problem, but you have the advantage that your photon remains focused for a long time. And that means that it can interact with many atoms along the way. So this has been shown in another talk, so there are several groups that have been working on this. The group of Okuta, this is from Peter Loda, the groups in atomic physics, on Borschenreuter, Kimball was mentioned, together with Oscar Painter. So there are lots of different kind of angles of this. We started this with molecules several years ago, and what we've done is to take something like a nano capillary. So you can have glass capillaries with openings of only a few hundred nanometers, and we fill this capillary with our organic matrix that contains these molecules. So you have a high density of molecules in the center of this capillary. The index of refraction of the core is larger than the surrounding glass. That means that your medium already works like a waveguide, and that lets you basically do this experiment in a very convenient way. What you see here is the part of the capillary that is butt coupled to a single mode fiber for convenience. In reality, it looks like a couple of 100 micron piece of fiber capillary. We clean cut the end of it and metalize it so that we can collect the light at right angles for convenience again in the cryostat. I just summarized the results to show you that this works. So what you see here is an extinction spectrum recorded simultaneously with a fluorescence spectrum. Fluorescence is the signal that comes on those redshifted channel, and extinction is really just a signal that is resonant with the system. You see in the extinction signal that, again, you reach a few percent of extinction. You have your narrow lines, and you also see very nicely that if you just tune your frequency a few gigahertz, you can become resonant with several molecules along the way. If you think about the beta factor, that is the amount of light that is coupled into the single mode for the type of index of refraction that we have, this beta factor turns out to be of the order of 18%. Experimentally, we could demonstrate 12%, so we're in the right ballpark. So all of that works. And now the question is, what's the next step? The next step would be to really realize a situation like this. The interesting point to note here is that the coherence length of the photon that would correspond to this 20 megahertz type of transition is of the order of a few meters, which means that in a type of a waveguide that is only a few hundred microns, all the molecules are seeing the same photon. The photon sees all of them at the same time. So it's very easy to get to the regime where you have a kind of a polaritonic coupling where the photon is completely superposed with many, many individual two-level systems. So what we now have to do is basically get all of these resonances to become identical so that we would be able to have a photon that interacts with all of these molecules again. What we want to do is put microelectrodes and tune all of these resonances to each other. At this point, we're leaving the nanocapillary type of geometry. One, because it's not very easy to put electrodes very close. But the other thing is that we would like to be able to scale this up, and so we wanted to do a chip-based type of experiment. This is the first try that we've had, so what you see here is in the middle a ditch, if you want, that we can structure on a glass chip. So this ditch would be then filled with the organic material and constitutes a waveguide, a sub-wavelength waveguide that will be going from here to here. These are the electrodes that you put on, so this is the counter electrode, and now we can look at this whole region. This is how the structure looks. This would be part of the cryostat that goes in, and this is an example of what you'll be recording. If you were to put your beam at one place on that long waveguide and just scan the voltage on one of the electrodes, what you see here is that you have lots of molecules at different frequencies, and each one of them is responding a little differently to the applied electric field, partly because they are embedded differently in the matrix, and partly because they're sitting at different distances from the electrode. This is an example of a case where we're looking at two different molecules sitting at two different places, and we managed to start tuning them to have the same resonance frequency. So all the building elements are essentially working, and the next step is to do something more interesting, and as a kind of a thing that would be more interesting is you can do all the things that are well known, any type of an integrated optical circuit that you want to build. These are now grating couplers so that they facilitate the coupling in and coupling out. Now you can bring these sub-wavelength waveguides and couple them to Western gallery modes or make interferometers or whatever. And by doing this type of thing and putting the Bragg type of feedback onto these waveguides, we think that we can get to coupling conditions of nearly unity, and then we would be really ready to do everything that we want to do. So to close, I'd like to show some of the calculations that we've done, which connects quite well to some of the talks, the theoretical talks that were presented before. And in particular, we have worried about the issue of disorder. This is a pretty rich plot that we won't be able to discuss in detail right now, but what we're assuming is we start with a periodic system and then allow for displacement of the emitters from there up to the point that they will be completely randomly distributed. So this axis is showing the degree of disorder, and this axis is showing the periodicity that you have. So there has been a lot of work in the atomic physics community on periodic structures, because this is what they can do very well. They can make lattices around these fibers. But when you're working in the solid state, it's very easy to have very large densities, much larger densities than you can ever have with gas atoms. And when you do that, then your atoms become very close to each other, which means that this dipole-dipole near-field coupling becomes quite substantial and important. So that's this space up here. And otherwise, what we have studied in detail is the localization effect. So you can say Anderson localization doesn't exist in this system in that way, but we do get localized modes. And we've studied that as a function of the beta parameter. So you know that if you have a perfectly one-dimensional system, you automatically localize, but this is an open one-dimensional system with a finite degree of loss out of the fiber, and all these things have been calculated. The last thing that I want to mention is something that we found quite interesting when we studied these things, and that's basically when you think that the photon comes in and undergoes multiple scattering from all of these guys. If you only have two of them, you basically form a cavity, because the light gets reflected from one atom and gets reflected from the second one and goes back and forth. You also get a resonance splitting because essentially you have a dipole-dipole coupling energy that is far field, but it gets mirrored into the spectrum. Now, if you have a whole bunch of atoms, it turns out that you get a mode splitting quite similar to what you know from strong coupling, except that strong coupling in the context of polaritons and essentially ensembles, it goes back to, I would say, the work from 1992, where people worked with quantum wells and showed that you can get something like a strong coupling in a cavity. Nowadays, people have talked and worked quite a bit on, for example, molecules on surface plasmons and getting a coupling. In all of these cases, the picture has been of two coupled resonators. What we find is that in this system, if you just have a whole bunch of atoms and consider them as one medium and send your light through this, just the fact that all of them are interacting with one mode, although there's no resonance associated with that mode, you still get a splitting of the transmission resonance. And that, of course, depends on the number of the atoms that you have. So if you only have one atom, this would be your absorption spectrum, and as you increase the number of atoms, you get a non-trivial type of resonance. So we still haven't completely studied this to depth, but we're interested in also doing some experiments on this to see how this would work. So with that, I'd like to thank you for your attention, and be happy to
So you see blinking in your molecules and presumably your other mixes as well. Do you see any spectral wonder as well? Is that them?
Yeah, so what you saw was not blinking, that was this frequency sweep.
Yeah, okay.
These molecules don't blink, they're really quite photostable, but you could get wandering of the spectrum if your crystal is not good.
Okay.
So you can easily mess it up and get spectral diffusion and spectral jumps if the molecule is not happy in its organics.
And do you see that in your experiments? What do you have to do in that sample?
It always depends. I would say that from 100 molecules that you look, you always have something of the order of 20 very little stupid things, and you just leave them alone and move on to the next ones.
Question at the back?
You see coupling efficiencies of about 12% at the moment. What do you really need to get to look at some of the really nice polarity effects? And how to get there?
Yeah, so I don't see any way that you will increase that to 100% in a simple wavelength. Simply because the intrinsic structure of molecules or any other system that is not a perfect two-level system would lead to a non-unity branching ratio, and therefore that number goes down. So, and then of course there are other technical things like the index of refraction contrast with which you build your waveguide, so you can play with that a little bit. But the strategy that we're pursuing now is to introduce a very weak kind of a bad cavity and add that to this waveguide. So what we think is happening is that what would be interesting is to get an intrinsically strong, efficient coupling just because you confine your mode to this one-dimensional waveguide. In addition to that, just add a little bit of feedback, a kind of feedback that doesn't have to be high finesse. So we're actually concentrating in several experiments on very low finesse resonances, because that allows us to couple all of our molecules to the same resonance of the cavity.
Last question from Christoph.
So the number of photons that we're collecting is of the order of a few hundreds per second, and a typical lifetime is of the order, depending on the transition you're looking at, could be 100 microseconds.
That's the last question. We have several talks to go, so thank you. The next talk is